Good morning everyone. We are going to discuss now about discrete Fourier transform and fast Fourier transform in digital signal processing. First we will see what is the need for discrete Fourier transform. So normally we will represent a signal in two ways. One is in time domain, another one is in frequency domain. So when we represent a signal in time domain, it gives the information about the existence of the signal and the shape of the signal. But when we want a complete analysis of the signal, that is, if we need the frequency spectrum, we have to represent the signal in frequency domain. So, in order to convert the signal from time domain, that is, say, if I have for a digital signal x of n, I have to convert it into time domain, say x of k. One of the tools used is the Fourier transform. And in this, for digital signal, we use discrete time Fourier transform. So, when we go for this discrete time Fourier transform, we are going to convert the continuous signal in time domain into frequency domain. So, the limits will be varying from minus infinity to plus infinity. So, when the limit is from minus infinity to plus infinity, the computation will be time consuming. So, I have to go for the other one, so in which we have to opt to discrete Fourier transform, that is DFT. So, in DFT we are going to limit the signal range, that is, we are going to fix the limit as 0 to n minus 1. Just I am going to truncate the limits minus infinity to plus infinity to 0 to n minus 1. So, now in DFT, to compute your x of k, the formula is sigma n is equal to 0 to n minus 1 x of n e power minus j 2 pi k n by capital N, where the capital N is the number of samples and small k, that is k and n, varies from 0 to n minus 1. Okay. So, now in this also we have a drawback, that is, here again the computation time is long, that is, suppose if for example if I take my k, first one as 0, so I will have my x of 0 is equal to sigma n is equal to 0 to n minus 1 x of n into e power 0, that is n also varies from 0 to n minus 1 x of 0 plus x of 1 e power 0 x of 2, like that. For example, if n is equal to 4, I will have my x of 0 is equal to sigma n is equal to 0 to 3 x of 0 e power 0 plus x of 0 e power 0 plus x of 1 e power 0 plus x of 2 e power 0 plus x of 3 e power 0. That is, for computing x of 0, I required 4 multiplications. I require 4 multiplication. Similarly, I require 3 additions. This is for one particular thing. The same thing is repeated for x of 1, x of 2, x of 3. So, in total I require, for n is equal to 4, for total I require, the number of multiplications is, number of multiplication is 16 and number of addition I require as 12. That is, in general, for n samples, here the complex multiplication is n squared and addition is n into n minus 1. Okay. So, I have to reduce this. So, one of the efficient way to reduce this is go by the algorithm base. That is why we go for the fast Fourier transform. So, fast Fourier transform, that is your FFT algorithm, we are going to use to reduce the number of computations. So, FFT algorithm is the one in which I am going to reduce the number of computation by adapting the algorithm. So here in FFT algorithm, what is the concept is that given any n sample, first thing is that I have to express it as r power m, where this r stands for the radix. This radix can be 2, 4, 8 like that, right? So first thing is that given the n samples, I have to represent as r power m. And in this FFT algorithm, again we have two types. One is your DIT, another one is your DIF, where your DIT stands for a decimation in time domain, another one is your decimation in frequency domain. So now we are going to see about the decimation in time domain algorithm, that is the DIT algorithm. Okay, so in this one, the first thing is that, what is the thing? This DIT algorithm or this FFT algorithm in general, it is called as your divide and conquer algorithm. Divide and conquer method, that is, what I am going to do is, given the n sample, I am going to divide it into subsections. My computation is also going to be done in the subsectional method, and finally I am going to combine to get the output. So how I am going to do that? So first thing is that here the n sample, first stage I will compute my r point DFT, right? Then this r point will be again carried out in r squared point DFT, then again r cube, like that, r cube point DFT, like that I have to do it till I get r power m, till I get r power m. Okay, so now suppose if I have my n is equal to 8. So first thing is that I have to represent it as some radix power m. For example, if I take my radix as 2, okay, consider my radix as 2. So how I will represent this? N is equal to 8 will be represented as 2 power 3. Right, so 2 power 3 I will represent it. So first thing is that first stage will be your, first stage is 2 point DFT, then the second stage will be, or here I can represent as 2 point FFT, and second stage will be your 4 point FFT, then the third stage will be your 8 point. So I have to stop till this because my number of samples and this is going to be the same. So I will be carrying the computation in 3 stages. First thing is 2 point, next is 4 point, then is going to be your 8 point FFT. Okay, so this is how I am going to compute my DFT for the given sequence using your FFT algorithm. This is the DIT, decimation in time domain. Right. So the next thing is that I have to do my twiddle factor calculation. So what is this twiddle factor? So we will see that, right. So that is, the formula for your DFT is x of k sigma n is equal to 0 to n minus 1 x of n e power minus j 2 pi k n by n. So in this, your e power minus j 2 pi, this is called as your phase factor or twiddle factor. So this is your phase factor or twiddle factor. Okay, so this one I can represent it as W. So e power minus j 2 pi k n by n will be represented as W n k n. Okay, so I have to multiply my input signal with this twiddle factor to get my output. So now in this FFT algorithm, we have to make the twiddle factor calculation in each and every stage, right? So we'll write out the proper steps now. So first thing is that in your FFT algorithm, step 1 is that find out the number of stages. Right? And step 2 is that I have to divide the samples. Suppose say if I have 8 samples, right? I have to divide it, right? So one of the easiest ways is that we have to divide the samples into even and odd samples. So even sample and then my odd sample. So when I go for the even number, it's going to be your 0, 2, 4, 6, and odd number, it is going to be 1, 5, 3, 7. So my sequence will be in the order, say 0, 1, 2, 3, 4, 5, 6, 7. So how to divide this even and odd? One of the easiest one is that you go for the bit reversal order. So in this, what I will do in my DIT, first thing is that given the sequence x of n, I will be taking it in the bit reverse order. So say it is going to be B0, B1, B2. Okay, so x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6 and x of 7. So now for 0 it's going to be 0, 0, 0. I am representing in the binary form 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So now I have to take it in the bit reversed order. That means just I am going to change the order. LSB will be turned to MSB and MSB to LSB. So when I do that, so what I'll have, so the same thing 0, 0, 0, and here this 1 will be shift over here. So I'll have it as 1, 0, 0, and again here 0, 1, 0, and here again 1, 1, 0, and here again 0, 0, 1, and here again the same one 1, 0, 1, and here 0, 1, 1, and this one will be your triple 1 will be the same thing. So this is 0, 4, 2, 6, 1, 5, 3, 7. So to compute or to execute this FFT algorithm, what I have to do, given my input samples, I have to take in the order 0th sample, 4th sample, 2nd sample, 6th sample, then 1st sample, 5th, 3rd and 7th. Right? So this is the next step. So next one is that the twiddle factor calculation, what we have seen. So what is that twiddle factor values? Right. So in this twiddle factor, in the first stage, you require the twiddle factor, that is W80. So everything we are speaking with respect to the 8 samples. So W80. So for that, it will be e power minus j2 pi into just this prefix part divided by this suffix part. So e power 0, that is nothing but my 1. Then for the second stage, the twiddle factor involved is W80 and W82, that is equal to again 1. Already we have computed. W82, that is e power minus j2 pi into 2 by 8. So e power minus j pi by 4, that is your cos pi by 4 minus j sin pi by 4. The value is going to be minus j, because cos pi by 4 is equal to 0 and sin pi by 4 is equal to 1. So I will have the value as minus j. And next is the third stage. So in third stage, I require my 4 twiddle factor W80, W81, W82 and W83. So now W80, the value is going to be 1, already we have found it. W82, it is going to be minus j, and W81, it is e power minus j2 pi into 1 by 8. So e power. So in the second stage, the twiddle factor values will be 1, and W82, that is nothing but your e power minus j pi by 2. So cos pi by 2 minus j sin pi by 2, the value is going to be minus j. And similarly for the third stage, the values are W80, which is equal to 1, and W81, if you compute, it will have it as 0.707 minus j 0.707. Right, W82 already we have computed as minus j, and W83 it's going to be e power minus j 3 pi by 4, which is nothing but your 0.707 minus j 0.707. Okay, so that is the thing. So now we have to do the computation. So before that, we have to look into the signal flow graph or the butterfly diagram for this DIT FFT. So given two samples A and B, for the first part here the computation will be A plus, that is this sample value A plus this value multiplied with this twiddle factor. In the downside, it will come as A minus B into WNK. So when we combine the two samples, this will be the flow diagram applied. So now based on this, we can draw the whole block of the DIT FFT for 8 samples. That is, first I have n by 2 point DFT, again n by 2, here again n by 2, here again n by 2. So here the values will be x of 0, x of 4, then x of 2, x of 6, then x of 1, x of 5, then x of 3, x of 7. So from this I'll get my n by 4 point DFT, and here again I'll have my n by 4 point DFT, and finally combine here I'll be getting my n point DFT. This is my output. Output will be in your normal order. Normal order in the sense it will be from your x of 0 to capital X of 0 to x of 7. So this is going to be the first stage, second stage, and then the third stage. Right? So this is how we'll compute the DIT FFT. Okay, thank you.